Good afternoon, everybody. My name is Dr. Fiona Jones, and welcome to this Oxford Sparks live Q&A. If you joined us over the summer, you will know that we did lots of these live Q&As as part of our Science at Home campaign. And even though that's now drawn to a close, we're super excited to bring you another one. If you are new here, then please do consider subscribing. It would be great to have you as a follower of ours, and that's the way that you can keep up to date with everything going on science-wise at the University of Oxford and here at Oxford Sparks. Equally, we're very active on social media, and you can follow us on Instagram, Facebook, and Twitter at Oxford Sparks. I'm really excited today to be joined by a physicist here at Oxford, Dr. Paolo Molignini, and he's going to be talking to us all about his work on topological materials. If you don't know what that means, don't worry, neither do I. We're here for the next half an hour or so to try and uncover exactly what it means, and I know that Paolo has brought along lots of interesting props that I'm really intrigued about. So I should also say just before we get started that we are live, so if you do have a question for Paolo, then please do just pop it in the chat box. Both of us will be keeping an eye on that. We'll probably aim to get to questions towards the end of the interview, but if you do have an absolutely burning question, then don't hesitate to pop that in and we'll see what we can do. So without further ado, good afternoon, Paolo.
Good afternoon, Fiona. Thanks for having me.
You're very welcome. So I guess a good place to start would be just to ask you to introduce what is your field of research. I obviously just touched on it, but it would be great to hear from your point of view.
Sure. So my field of research is theoretical physics, and I work at the interface between condensed matter and quantum optics. So condensed matter deals with everything which is in a condensed state. So those are materials where we have large number of electrons or atoms interacting strongly with each other, and they give rise to a macroscopic recognizable phase such as solids, crystals, liquids, but also more kind of exotic stuff like magnetism, superconductivity, and topological order, which we will talk about today. And on the other side of my spectrum, there is quantum optics, which deals with light interacting with matter at a submicroscopic scale, so where light behaves as photons, so like chunks of light. And that deals with lasers, cold atoms, trapped ions, optical lattices, so all this kind of laser stuff.
That sounds super exciting and really interesting. Obviously, lots of really cool sounding words in there. What do you do on a daily basis as part of your research life? If you were going into, if we weren't in lockdown and you were going into the lab, then what would you be up to or at your computer?
So luckily, even in the lockdown, my life was kind of the same work-wise because I mainly work with pen and paper and computer, so I can also do that at home. So the idea is that we want to try to discover new properties and new phenomena in physics. And so we come up with models to describe the systems that we look at. And then there's always a trade-off between how accurate the model is and how complex it is. You always need to have a method to solve this model. And either you do it by hand or by using simulations computers. And once we verify those theoretical predictions, we try to apply them on experiments. Then I pass the ball to the experimentalists, and they try to develop prototypes and experiments to verify those findings that we try to look for in theory. Then, of course, the ultimate goal is to try to come up with some useful technological application for that exploits the new properties that we find. As an example, we will talk about it later. There's these edge states that appear in topological insulators and the superconductors that can be used in electronics or quantum computers.
Brilliant. So yeah, we'll get on to that in a moment. But I guess as the person coming up with kind of the theoretical concepts and doing the modeling, even though you then pass the ball, as you say, onto your collaborators, you must be super interested to see the results of those experiments and see what happens.
Yeah, of course. And often there is a strict collaboration between theoreticians and experimentalists once the experiment is running, because you get data from the experiment. You always have to refine your model, and interpret the data. So there is always a lot of back and forth.
Of course. Yeah, so you don't just leave it there, you get to stay involved. Well, I guess we should dig into the topological materials a little bit more. Let's start at the beginning. What exactly is a topological material or system? Break it down for those of us who don't have a clue.
All right, so this is a rather broad term. So this is a material that has special properties that arise from the topology of their quantum states, and the key word is topology. So topology is a branch of math that studies the properties of geometrical objects under continuous deformations. That means under bending, stretching, twisting, but not cutting or gluing.
Okay.
So we can sort these objects depending on their topology, and then we can divide them into topological classes which have different properties. And maybe to be a bit more concrete, I brought, I don't know if you can see it.
We love objects, yes.
So there is a teacup or a coffee cup and a saucer. So those belong to different topological classes because I cannot deform the teacup to make it into the same shape as the saucer. And this is because we have a hole here in the teacup. And of course you say, well, how can we deform a teacup, right? It's a solid object. So to show this, a mold with the Play-Doh, which we can actually deform. So I can show you that if I try to squeeze this, right, I can try to make it into this like flat shape, like the saucer. But the problem is that I will still have this hole here. And I cannot remove the hole unless I break it, I cut it. And this is not a transformation that is allowed in this continuous transformation that we spoke about. So another example that I have is the famous Möbius strip. This is just like a regular strip that I colored with two different sides. So we have two ways of putting this back together. Either we do this, we glue the same sides such that we have a red outside, the green inside. This is one possible topology that we can create. Or we can glue them, we can glue the sides like this, upside down, and then we obtain what is called a Möbius strip, which has a different topology and different properties. And in particular, it's very cool, it has no inside and no outside. Because if you run through this like red surface, you will see that eventually you end up on the green part. And then you do another round and you end up again on the red part. So the red and the green is actually the same. It's the inside is the outside. So this is a different kind of structure that we can obtain.
Yeah.
So we can have something similar also in band theory for materials. So what is band theory? So quantum states and materials have also different topologies because their bands can have different topology. And an energy band in a solid is just a way of mapping out the energies that the electrons are allowed to take. So you have to imagine in a crystal, right? We have like a regular arrangement of atoms or ions. Those form like the skeleton of the, and the electrons are sort of smeared out in the orbit around them. But the electrons and the ions are interacting with each other. And because of these interactions, the electrons cannot have an arbitrary energy. They are confined in energy bands. And these bands can tell us how we can populate the electrons in terms of energy. And actually, it's what gives rise to the distinction between an insulator, so a material that does not conduct electricity, and a metal that conducts electricity, like iron and so on. And I made a small Play-Doh model of this. I hope you can see it.
Brilliant. Yeah, if you just tilt it up a little bit. Don't want all the balls to fall down.
Exactly. Those are supposed to be my electrons that are escaping. So this
Perfect.
blue and the yellow, those are two different bands.
Mm-hmm.
The lower one is called the valence band and the upper one is called the conduction band. And another important concept that we need to know is what is a Fermi level. So this is the maximum energy that an electron can have. And depending on where it lands on this diagram, we can have different properties. So another thing is that these bands are separated from each other by this band gap. And this is a so-called forbidden band. And here, no electron can live. So we can only populate this lower band or the upper band. So what happens if we have our Fermi level, so our maximum energy, somewhere here, right, where the upper balls are located? Then it means that this area is empty and the electrons can kind of move freely around. So this is actually what causes electrons to conduct, because they can move around very easily. But if we remove all of these electrons, and we have, oops, balls falling all over, and we have the Fermi level here, then we see that the electrons need to have like a bump in energy to go from this lower band to the upper band. So that's why these materials with this type of band structure are called insulators, because there is no way that these electrons can conduct electricity because this level is already full. And they would need to hop over here, but they will require like an extra boost of energy, which they do not have unless you apply some electric field, some other perturbation externally. So this is kind of our picture of how we explain how insulators and metals work or described. Now, coming back to your question, what is a topological insulator or a topological material? So it turns out that these bands can also have a different topology, like the Möbius strip that I showed before, or like the teacups. They can have a different shape. And so if we compare it to the right side, we can have the situation where the bands cross like this. And this can be caused by what we call spin orbit coupling. So the spin of the electron, which is some sort of inherent magnetic moment that the electron has, interacts with its own orbital motion and makes these two bands overlap. But what happens actually is that because of the interaction, they form a different type of structure that looks like this. So we see that there is a change in color here. We have a part of the blue that goes to the yellow and vice versa.
Yeah. And
we can see, so this is a different topological structure because because we have a different occupation or different geometry of the band structure. So this is what characterizes a topological insulator. It has a different structure of the bands, which is called the band inversion, because we are inverted the bands. And the cool thing is that if we have these two materials together, like a trivial insulator here and a topological insulator, the only way to merge them together, like we said before with the Möbius strip, the only way to go from one to the other was to cut it, right?
Yeah.
Or like the teacup was to just break it. So the way that we break this structure and we merge one to the other is by having an interface. So for instance, by sandwiching a topological insulator between two different insulators. And what happens is that then at the edge, we have states that have to connect the yellow with the yellow and the blue with the blue. So we have something like this red states here. And those states are localized precisely at the edge, hence the name edge states, between the trivial insulator and the topological insulator. And remember, we said that the Fermi level is around here. So while the two bands are not conducting their insulators, these states are precisely at the Fermi level and they can conduct electricity. So we have this very peculiar situation where the bulk is insulating, but we have edge states on the boundary that can conduct electricity very efficiently. So this is kind of, in a nutshell, what the topological, in this case, topological insulator is.
Brilliantly explained. I've been on the screen, I don't think, but I've just been here nodding along and going, because yeah, it helps so much to have those visuals. So thank you so much for preparing that. So, I mean, you've kind of touched on it a bit already, but what is so special then about the topological insulators when it comes to their properties and maybe their uses?
Yeah, so as I mentioned, one of the characteristics is this presence of these edge states. So those are states, as I said, that they live only exclusively on the surface of the sample if we have a 3D object. But we can also have a 2D object, like a 2D, like a very thin sheet of material. And then in that case, they live at the boundary of this 2D sample. And in a 1D system, so in chains, then they live at the ends of the chains.
Perfect. I know you sort of touched on it a bit already, but people like me who maybe need to digest all of the information is really useful. So do you always need to have interfaces to have these edge states?
No, because you can think of, I said before, sandwiching between two trivial insulators, right? But you can also think that air or empty space is also a trivial insulator. So you can think of just the material alone on the boundaries. It interacts, it has an interface with air, with the space, vacuum space. So that's the boundary of the material, and the edge states then are localized there.
It's quite a sort of abstract thing to get your head around, but yeah, that makes sense. So I know that you also said you work on topological superconductors as well.
Yeah.
Can you tell us a little bit about what these are? In fact, I should just say, in case I forget at the end, that you've produced 3 fantastic illustrated explainer videos all about superconductors. So I would strongly urge you, if you're watching after this, if you're still keen for more, and I'm sure you will be, do check those out. They're on our YouTube channel. So your place. And I'll say again at the end, but sorry to interrupt. Continue to tell us about topological superconductors.
Yeah, so as I've shown in the video that some of you might have seen or will see, superconductors are materials that can conduct electricity without dissipation. This happens only below a certain temperature, but the main property is that they have this like wonderful property that you can conduct electricity without any resistance. So the superconductors that we know, those are elemental superconductors, like elemental lead below a certain temperature. They are described by microscopically by what is called the BCS theory. The name stems from 3 physicists that came up with it: Bardeen, Cooper, and Schrieffer. And so within this theory, what happens within a superconductor is that electrons pair up and form Cooper pairs, which have different quantum properties than electrons, and they are bosons, and they can condense into a sort of fluid that can conduct electricity without bumping into anything, and therefore you have this like perfect conductivity. So in superconductors, the Cooper pairs form the stable states, like the standard way that electrons want to be in. And once you break them up, these electrons, they are in an excited state. So these excited states have to fulfill a certain symmetry, which we call particle-hole symmetry. And this is also reflected in the band structure that I showed you before. It has like additional properties. So a topological superconductor is a superconductor that has this particle-hole symmetry, but also has these band inversions that I showed you before, right? This like blue into yellow and vice versa. So if we have these 2 ingredients, the superconductivity and the band inversions, the topological nature of the band structure, then you have a topological superconductor. And so this can be achieved again with this spin orbit coupling that I mentioned, with magnetic fields, with various techniques. And like for topological insulators, you also have these edge states at the boundaries of a topological superconductor. And one of the very cool things about topological superconductors is that their edge states have very, very unique properties. They can be what we call Majorana fermions, which are their own antiparticle. So those are particles that are localized at the ends, and they behave as their own antiparticle. So those are particles that were predicted in the 20s by Ettore Majorana, hence the name Majorana fermion. And they were actually first developed or discovered in particle physics, but in theoretical particle physics. But so far, they were never found as free particles in experiments. So there is some speculation that maybe neutrinos can be Majorana fermions, but there is no conclusive evidence. And so the cool thing is that in our topological superconductors, so in our materials, we can actually we can engineer a solid state realization of these like exotic Majorana fermions.
Brilliant. I think this has got to be whetting the appetites of any aspiring physicist that we have watching. There is nothing like a lunchtime discussion like this.
Physics with superconductors.
Exactly. Amazing. As always, the time is flying by. Always does when you're having fun. Do you have any research data that you could show kind of these band structures and edge effects? I think you hinted earlier that you might be able to share your screen.
Yeah, I will share my screen now.
We'll
just
wait a moment. Yeah, there we go. I can see myself.
So I have some examples from 1D materials and from 2D, two-dimensional materials. So this is actually not a topological superconductor. This is a different type of model, but it shows you this like localized edge states. Here on the right, you can see this is the localization along the chain of these states that are called edge states. And so on the left panel, you actually see as a function of a parameter how these energy bands behave. So we have the conduction band and the valence band, the blue and the yellow that I showed you before. And you can see as we change a parameter, we close the gap between the two bands, and then we create this mode at zero energy. And this is precisely the edge state that we see on the right, which is localized at the edges. I also have some more data for 2D that maybe shows the localization a bit better. This is precisely the kind of the figure, the plot that I showed you with the edge states with the Play-Doh. So we have the conduction band, the valence band below, and as a function of momentum, we see that we have these edge states that appear and that cross between the two bands, and those are the ones that can carry electricity. And if you look at the localization of these states, you see again they're really localized at the edges. They want to be at the ends of the sample. Mm. And I also have a cool movie that I can show you.
Yeah, let's give it a go.
So this is actually a slightly different system. It's a periodically driven system, but the principle is the same. We have bands. And so as I scroll through the movie, I'm just changing certain parameters in the systems, and the bands also change shape. And we see that we have the appearance of these edge states as well here on the left and on the right. Mm. So it's here and here. And yeah, I mean, the band structure of these systems can be pretty complicated and pretty, have a lot of transformations as we tune the parameters. So what we really try to do is kind of use this like weird shapes and properties to get to some intriguing applications.
Yeah, absolutely.
Maybe I can show you the last thing, where you can actually see it on a 2D plot, the difference between what is called a bulk state, so a state that is localized uniquely within the band, and you see here it's really like a blob. So this is your system, right? It's a finite size, and it's really like a blob all over. But if we look at edge states, we see that they really are at the boundary.
Mm.
They really are very well localized. But yeah, those are some of the plots that we generate on a daily basis.
Yeah, thank you so much for sharing those. It is always really useful actually to see a visualization. So that's brilliant. You also get a sneak peek at Michaela, who is in the background doing all of the behind the scenes technical wizardry. So thank you to her. Brilliant. So, I mean, I think people might find the concepts that we've talked about quite abstract. Are there any more concrete examples of what a topological material is? Is it something you could find in everyday life, or is it something that's more complex than that?
So, as I mentioned, I personally focus more on mathematical models.
Yeah.
So I pick up the properties that we want from scratch. It's like, it's like cooking, really. Just take a bit of flour, a bit of sugar, and then you have like a pie, which is something completely different than the ingredients, right?
Yeah.
So in a nutshell, no, they're not everyday materials, because we really want to make like these properties or get these properties together in a very calibrated way. So what we usually have in an experiment are heterostructures. So those are nanostructures composed of different compounds, different materials that are put together in a very specific way to achieve the properties that we want. So one example is so-called quantum wells. So those are layers. So the famous experiment that showed, the realization of a topological insulator, those are layers of cadmium and mercury telluride that created the sandwich structure that I showed you before, with the two trivial insulators at the at the sides and the topological insulator in the middle to get the edge states at the boundaries. Actually, in the past few years, we are starting to slowly discovering elements or compounds that are topological insulators on their own, which is pretty cool because we don't have to manufacture them, by hand.
Yeah.
So one of those is our bismuth alloys with antimony and selenium, for instance.
Okay.
And bismuth itself is a so-called higher order topological insulator, which means that it has, instead of edge modes, it has hinge modes. So if you think about like a cube, like a 3D material, these edge modes live at the hinges of the sample. They're not on the whole surface, but they're only on the hinges.
Yeah. Interesting.
And so for topological superconductors, things are a bit trickier again, because for a topological superconductor, we need to merge superconductivity and magnetism, which, if people have seen the videos, they know that superconductivity and magnetism, they don't like each other. They don't want to be together. So it's kind of tricky to make them interact with each other to realize the physics. So what people have done is to deposit magnetic ions, like iron, on a superconducting substrate, like lead, or they can. They also used semiconductor nanowires that are embedded into a superconductor, and also there is a magnetic field applied. But those are just kind of heterostructures that are kind of, again, cooked up from scratch to have these certain properties.
Yeah. Oh, really interesting to hear about the bismuth. But yeah, we're not going to just stumble across a topological material, maybe.
Well, yet, right? We never know. But so far, what we know is that
as yet,
a bit more complicated. Yeah.
But we know that donuts and teacups and things can be very, very good to explain what a topological material is. So I guess as we come towards the end, people might be wondering, all this is really interesting and well and good, but why are these materials actually useful? So yeah, could you tell us a little bit about what applications they might be used for in the future?
So yeah, they actually have a lot of pretty cool applications. They're in their developmental stage. Of course, we do not have functional prototypes yet. But so one way that we could harness these edge states is to conduct electricity more efficiently. So that could, of course, lead to economical and environmental benefits by lowering the energy consumption of our computers, electronics, and so on. So if you think of a normal wire, right, the whole wire conducts. There's the bulk conductance. And there is friction because the electrons, bump into each other, bump into like other stuff. So there is energy that gets lost. For a topological insulator, you can actually have only these conduction channels, conducting electricity, only at the surfaces, and then the bulk stays insulating. And so this could be used, for instance, for new type of transistors or new type of electronic devices and current carriers in electronics.
Yeah.
Some of those actually are spin polarized currents, which means that you can selectively choose electrons which has a certain spin up or spin down. So you can engineer also new transistors which are based not on the charge of the electron but on the spin. So this is kind of like a new level of technology that you could develop. And also, that's something that I didn't mention before, these edge states are protected by symmetries. So the twisting and bending of the band structure with perturbation does not change the topology and the properties of the edge states as long as you maintain the symmetries. And because of this robustness, the edge states are they're very good. They have very good coherence, we say. So they persist and they're very stable. And even if you add random defects at the boundaries, you can actually see also in experiments that the edge currents would just automatically circumvent the defect. So really, they go around it on their own.
Yeah. Wow. Super impressive stuff.
Sorry, go ahead.
No, I'm just making noises of being impressed. So,
so for topological superconductors, that's also, apart from, I think, in my opinion, the cool realization of this like Majorana physics that was not observed in particle physics so far. The Majorana end modes are also possible building blocks for quantum computers, so-called topological quantum computers. They form so-called non-abelian anyons, which is a very fancy word to say that if we exchange two of those particles, we do not get the same state, but we have a sort of a knot or a braid that is formed. And we can use this braiding to encode quantum information. And also because of topological protection, this braiding cannot be undone by local perturbation. So I can perturb one Majorana here and the other Majorana there, but as long as they are not exchanged again, the information is stable and it's like conserved. And so if you have like an array of Majoranas and you just interchange them all together, you can construct a very stable register for a quantum computer.
Yeah, that's so important. From what I understand about quantum computing, it's very sensitive to the environment. So yeah, to be able to have that protection would obviously lead to some very exciting things.
Yeah, no, it's a very exciting field to be working in, for sure.
Yeah. Well, actually, that leads me on quite nicely to my last question, which is, how did you get into this field? Have you always been interested in science, physics specifically, or yeah?
As a child, I wanted to become an astrophysicist. Then I wanted to become a doctor. And then I started studying civil engineering. And then I said, no, I really want to do physics. So I went back to physics. But yeah, I always had like a passion for science. And actually this passion kind of grew through looking at this like popular science programs on the TV. And I thought, oh, wow, they're doing so many amazing things, with science. So I always felt connected to that. And in regard to the condensed matter aspect, I was actually drawn to topological material because of this discovery of Majorana fermions. I thought, wow, I mean, they cannot measure these particles in free space, but they can actually realize it in a condensed matter, like in a material, like in a chunk of something. And I thought that's really cool. So I was drawn from these discoveries.
That's brilliant, and also encouraging to hear. You sort of went off in a slightly different direction and came back to physics, and sometimes things work out like that. And you're obviously really super at explaining things, and you did some, as I said in the middle of the interview, some videos for us. Did you just want to do a little pitch for your videos? And
yeah, sure. so those are really like short videos. They're like 3-4 minutes long, so you can really watch them, while you're on the bus or while you're, having your lunch. So I basically just I was, stuck as everybody else in lockdown, quarantine. So I thought, okay, what can I do to, occupy my time, my free time? So basically, I just drew everything by hand, and I filmed it with an iPhone, just stuck on like a stack of books. I put it up on top, and I just filmed myself drawing, and then I recorded the audio, and then I just put everything together with iMovie, and that's it. It's not really hard, actually. Everybody can do it.
They look awesome, and you do lovely drawings. So I would honestly urge people to go and check them out. And we've put the link in the chat box, so you've no excuses. Easy link through. Brilliant. So we did have a question come in. I have to apologise to Quantum Cinema because it came in a few minutes ago, so was sort of linked to what we were talking to at the time. I don't know if you can explain at all, Paolo. So you were talking about single electron things. Do the electron-electron interactions affect the physics at all, and how? You'll be in a better position to interpret that question than me.
So basically, the question refers to the fact that I explained a type of physics which is called in the single particle physics, where the interaction between the electrons are kind of neglected. And with some sort of mathematical transformation, you can bring back everything to what is called a single particle picture. So as if you had just one particle moving in a certain potential. And the usual topological properties are, or the theory was developed for this type of physics at zero temperature with like no interaction, or when the interaction can actually kind of be hidden away. The question now refers to what happens when you add interaction between the electrons or between the particles. And of course, this is a very active field of research. There is some evidence that there is still stability, so you can still have topological features, but they're kind of slightly modified. Another thing that can help to stabilize this topological states is if you add disorder. So if you have some like random noise, there is evidence that you can stabilize certain phases, topological phases, with that. But so this is a very active field of research because we do not have a lot of methods to analyze the full interacting problem. It's a bit more complex. So typically people use more computer simulations to tackle this. Mm-hmm. And there is no like a theory, a pen and paper theory that is very like overarching and explains the whole thing. But yeah, it's a question that we will have to eventually address really fundamentally, because in a real material you have all sorts of interactions, so you really have to address that. And the key question is the symmetry preserved? One of the symmetries that I was telling you about.
Yeah.
So yeah, there is still a lot of research to be done there, but it's an interesting question.
That's always exciting, though. It's nice to hear about the next future questions that we need to tackle. So yeah, brilliant question, Quantum Cinema. Thank you very much for sending that in. So I should say, I mean, it's not always possible for people to be tuning into these live things when they happen, but this will remain online. And Paolo has kindly said that if you do have questions for him, you're welcome to tweet them to him, and it's at P Molignini. I've been tagging him in our posts about this particular interview, so you can find it on Twitter. Quantum Cinema says thanks, so you're very welcome. So yeah, if you do have questions, do feel free to tweet them, and if you would like to find out more about superconductors, do check out the videos. I think that's all that we've probably got time for, unless, Paolo, did you want to add anything about anything?
No, I think I'm good. I mean, if anybody has further questions, they can always tweet me, and I'll try to answer it as good as I can.
Brilliant. Yes, I think you've covered everything. It's been really interesting and great to hear from you. And thank you so much for joining us. I know you're joining us from Switzerland, so extra special thank you amongst everything going on at the moment. So thanks for joining us. We don't have any other live Q&As lined up at the moment, but we might well do soon. And we've also got podcasts and animations and other videos for you to check out. So as I said at the beginning, do consider subscribing to us here on YouTube or following us on social media. And other than that, we'll hope to see you soon. Bye-bye.